In this video, I'd like to connect some dots with some of the various things that we've been learning about calculus in the last couple videos in this series with what our initial goal was at the beginning. So if we go back all the way to the beginning of the series, you might remember that we basically went over the problem that Isaac Newton was trying to solve, and we sort of explained how if you have some object and you basically let go of it near the surface of the Earth, then it will accelerate downwards at a rate of 9.81 meters per second squared, or meters per second. So in other words, we have a constant acceleration. That's what Newton's laws of physics tell us, specifically his law of gravity and his basically laws of motion, the second law of motion specifically. And our entire goal throughout this course was to basically develop sort of a new a new way of mathematical reasoning to basically get from the acceleration to the distance function. Because if we can determine a distance function based on this acceleration function, then that means at every single point in time, we will know exactly where the ball is. That means we can predict exactly how it will move, exactly where it will be over various points of time. And that's sort of the whole goal. That was the entire goal that we started this lesson with. So I want to basically uh, start with the fact that we start, so basically we start with this distance, and then we said, okay, if you take the derivative, let's say derivative, that'll get you to the velocity function. And if you take the derivative of that, that obviously gets you to the acceleration function. But in terms of the physics, we're actually given the acceleration function and we want to go backwards. So we want to take the integral to get to the velocity from the acceleration, and then we take the integral again to get to the displacement or the distance. Or it's actually the displacement. That's more accurate to say displacement. But that's what we actually want to do in this video. So I want to actually take the acceleration function that Isaac Newton says is what describes our reality and basically combine it with the calculus that we've been developing to come up with this displacement function. So that's what we're going to do in this video. Let's just go down here, and we're basically going to start with, a of t equals 9.81 meters per second squared. And we're basically going to take the derivative of that. So and that's going to give us the velocity. And by the way, I know in the previous video we talked about the basically the difference between definite and indefinite integrals. I'm just going to work with the indefinite integral in this video, not worrying about the bounds, just so you can see the sort of pattern that pops up. So this is what we learned throughout the series. Basically, the velocity function is the integral of the acceleration function, and now we're just gonna actually try and find out what that is. So what are we talking about? We're saying 9.81 times dt, where 9.81 is obviously a constant. So we're basically just integrating a constant, which we know how to do. We did it in the previous video, and you can also use the inverse of the power rule. You can basically see this as 9.81 9.81 times t to the 0th power. And then if you take the kind of the opposite of the power rule, what you'll end up doing is you'll be increasing that degree by 1, and then you'll be sort of dividing by 1. So long story short, the integral of this function is 9.81 t. Now, this is not exactly true, and I want to sort of get to a nuance that I sort of intentionally left out in previous videos, and that's that it's actually this plus some arbitrary constant c. And if you think about this, does this make sense? Basically, we'll take the derivative of vt, so let's take the derivative of vt, and hopefully we get this. So, we take, 9.81 times t, that's like the power rule, so this is t to the first power. We'll drop the 1 down. So 1 times anything is that thing itself, so the 1 won't show up here. But then we'll decrease this power to 0. So we'll end up with 9.81. And if we apply the integral to this term, and that's another property of the integral, by the way, the integral of sums. So for example, the integral of sums of two functions is equal to the sum of the integrals, basically. That's essentially the property. So that's sort of the property that I'm invoking here. This follows from the derivative. So this is also true of the derivative, and the fact that it's true of the derivative implies that it's also true of the integral. I didn't really get into the details of why that is in this course, but this is sort of a standard rule that's covered in a normal calculus course, which is why I didn't really get into it too much. But anyway, so if we just applied we just applied the derivative to this. Now let's apply it to this. What's the derivative of a constant? Well, 0. So we actually do end up with what we started with, 9.81. Now you might notice that this c could actually be anything. It doesn't matter what the constant is. When we take the derivative of any constant, it's going to be 0 because it doesn't change. Remember, the kind of the intuition behind the derivative is the rate of change of something. If something is constant, no matter what constant it is, it doesn't change. So it's 0. The derivative is 0. That sort of makes sense intuitively, I think. But anyway, basically what I'm trying to get at here is that this constant can be arbitrary. It can actually be anything. So for example, if we had, v of t, or whoops, if we had v of t equals 9.81t plus 5, or 10, or pi, or anything, any constant, anything that's not dependent on t, take the derivative of all of those, and they're all going to get to 9.81. So in one sense, this constant is arbitrary. That's why it's called an arbitrary constant. But there is a way to solve for it. So if we think of we have this 9.81t plus c. There's one way to solve for this, and if you get clever, and that's basically to sub in for t equals 0. So if we start off at v of 0 equal, what would that equal? That would be 9.81 times 0. So this whole term is going to vanish, and you'll be left with c. So in one sense, the constant is actually equal to what the velocity function is at 0. We usually denote this with, as a number with v subscript 0. This is what you'll see in, sort of a physics class where you're learning Newtonian physics. But, I think it would be good to leave it at that. So this arbitrary constant is actually v0. So, all right, let me add that. So our new formulation is that the derivative of the indefinite integral, I should say, not the derivative of our acceleration function, is going to be 9.81 times t plus our initial velocity. So there we have that. And this is also, by the way, going to be equal to our velocity function. So we have our initial velocity, what we start at, and then our velocity increases linearly. If our acceleration is constant, that means we have a linearly increasing velocity. So for example, if you think of, let me try and draw this here. So if this is the acceleration graph, and say we're talking, this is a constant. All right, let's make it a straight line. This is a constant. That implies that this function down here, the velocity, so this up top is the acceleration. This velocity, it implies that it's basically a function like this, where the equation is c times t, where c equals 9.8, and 9.81. And you can imagine we can change this offset here, this constant term. That's where this arbitrary constant comes in. It's essentially the y-intercept, and that can shift up or down depending on where you start. And all these are actually valid solutions to the integral. All these lines at different c's. That's sort of what we mean by the arbitrary constant. And the way that we determine which one to actually pick is to set t equal to 0 and basically solve for it. And that's how we actually would determine it for a real problem. Anyway, so we just sort of went backwards, and now we have this v of t. So now if we take, the integral of this again, which remember is what we want to do to find the actual displacement function, well, let's do that again. So let's do the power rule in reverse. So we're talking, 9.81 over 2 t squared plus v0 t plus another arbitrary constant. So this is the distance. And by the way, I should have actually started this video saying negative 9.81 to indicate that negative means going down towards the ground. So if you let your ball fall towards the earth, earlier we were using, we're making towards the earth be positive in a way, be negative, but in a normal physics class, it actually they actually do it the opposite way. So I just want to kind of go over that convention. They actually consider getting further away from the earth as the positive direction, and negative, or down towards the earth, as the negative. Attractive forces are considered negative in physics. So I think I should just start using that convention here. But anyway, we get this. So, we sort of understand how all this works, except for this c, this arbitrary constant. We have a polynomial. All these other terms have t, so how would we actually find out what that c is? Well, we could sub in t equals 0. So that would cross this term out, because that has a t squared here, so that would be really 0 squared. And then it would cross this one out as well, and we would just be left with c. And we would denote this by some number x initial. That means rewriting this, we would really end up with something like this. So talk about, and if you divide this by 2, by the way, that's going to come out to about 4.9. So not exact, but approximately 4.9 t squared plus v0 t plus x0. And this is the distance equation that we originally wanted to find out. This, if you take a ball and you basically drop it to the earth, you can use this equation. This is actually a simple quadratic. It's very straightforward. You can actually solve this equation with basic algebra. You can actually tell when the ball is going to hit the ground. You can tell how high the ball is going to be. Obviously, in this case, the highest it will ever be is the height that it starts at. But you can actually tell a lot of these things, and this is actually the basic equation of sort of mechanics. This basically describes a parabola, which basically describes motion in the motion of objects in a gravitational field. Now, to actually apply this, I just want to do some basic applications so you get an idea. And by the way, this is not, you might not see this equation in like a normal calculus course, but you will see it in a physics course. And just know that the way it's actually derived is with calculus. And that this is how Newton sort of bridged the two worlds. He basically came up with calculus so that he could make more progress in physics, and that's why Newtonian physics is named after him. It's all really based on applying calculus and his law of gravity and his laws of motion to kind of come up with kind of a new field that builds off the previous things that he did. So anyway, in this particular case, the initial velocity would be 0 because we're just letting it go. We're not a non-zero initial velocity would be if we threw the ball up in the air or down towards the earth. So down would be like a negative initial velocity, and throwing it up would be a positive initial velocity. But we're just assuming we let go of it, so there's no initial velocity. So realistically, the way this would work for our purposes is that we'd have 4.9 t squared plus 0, which is obviously not needed, and then we just have this x0. What is this x0? The initial displacement. Well, obviously it's this height, so this height here is x0. So I'll just replace it with height so that you understand. But anyway, the way that you would determine it's essentially a quadratic that's simpler because it doesn't have this initial term. So for example, if you wanted to find out, I don't know, let's make it simple. Uh let's say that the height was exactly 4.9. Eh, yeah, let's just use that. You can actually find out let's say for example the height was, you know, was 4.9, and you wanted to find the time such that this equaled 0, such that your displacement, because remember, you're starting at your initial up here, and you would say, okay, when do we hit the ground? Well, we hit the ground when x of t, the displacement above the ground, is 0. So we would set that equal to 0. Then, just going through the algebra, you'd have 4.9 equals 4.9 t squared. Divide both sides by 4.9, so you would end up with 1 equals t squared. Take the square root. T. Time of -1 doesn't really make sense because we're not running time in reverse. We're restricting the domain for the time to all positives, so we're get rid of that. So basically, what this tells you is that if you start off 4.9 meters above the ground and drop the ball, it'll hit the ground in exactly 1 second. That's the implication of Newton's equation. Just use it using actual numbers, and you can plug in different numbers here. We can actually um, generalize the amount of time it takes to fall by just basically assuming we don't add an initial velocity to it. So we would do that by basically setting this equal to 0, and then we have this, obviously negative 4.9 t squared plus h, and then we basically just solve for t. So I'm just gonna skip a couple steps, but basically t equals square root of h over 4.9. So if you have any h that you start with, a starting height, and you want to say how long does it take to hit the ground, well, this, assuming you don't throw it up or down, but you just let it go, you just drop it. This equation will actually tell you how long it takes to hit the ground in seconds. And this is very powerful. This gives us a lot of predictive ability. This doesn't only explain falling objects, it's actually a lot more complicated than that. What it also explains objects that you like throw. So if you think of a person who throws maybe a football, throw a football. It's not a very good football, but just imagine it in the air. Let's call this x initial. This equation basically says the ball is going to follow a parabola until it eventually hits the ground. And you can I'm not going to get into this in too much detail. And the velocity that you throw it with initially is v0. That's basically how hard you throw it. Um, I don't want to get into vectors too much, but that essentially has a horizontal and a vertical vector component, and you can sort of break the problem down that way. But that's sort of getting into like a basic physics course that I don't want to really get into now. But I just want you to understand that this equation right here, this parabola, is a lot more general than just dropping objects. It can handle throwing objects too. But it can basically handle how any object near the surface of the earth moves given certain initial conditions, basically how high you start and how hard you throw it and in which direction. Using this and some of the basic tools that you learn in a sort of introductory physics class in college, you can calculate a lot of things like how high the ball is going to be at each point in time, when exactly it'll hit the ground, all sorts of things. So I just thought I'd mention that to sort of connect the dots between how does calculus. We started this whole series with trying to develop calculus in order to use Newton's equations for physics, and this is actually how they apply after we've sort of built up the tool set for calculus. So I just thought I'd share that with you.